Hello class, this is a video on radian measure and how to convert between radians and degrees. And in this video we're going to learn what a radian is and how we can go back and forth between the radian and the more familiar measure of an angle, which is a degree. So you're probably used to degree measure, meaning like if I started right here at this point and I rotate it all the way around, that would be 360 degrees, being a full circle, right? And then if I stopped, like for instance, let's say I stop right here, I rotate from that starting point up to here, you're probably used to calling that 90 degrees, right? And that's fine, but in higher level math, especially calculus, we describe angles a lot of times with a different measure, and that's called a radian. Right? And what a radian is, what the measure of a radian is, let's say that this unit right here is 1. Right? It's radius 1. Well, because it's radius 1, what I want to do, my goal here, is I want to start from that red point. I want to start rotating. And notice as I rotate, this distance right here, this arc length is growing. It's getting bigger and bigger and bigger. So as I rotate that point, I'm getting a bigger and bigger and bigger arc length cut out. Now, what my goal is I want to keep rotating this point up until the arc length that I've cut out, it's got a bend in it, but I want the distance that's cut out by that that point being raised from here up to here, basically that distance that upper point travels, to be the same as the radius, which is 1 unit. So if I keep rotating all the way around, eventually I'll go far enough to where I'm pretty close to this distance right here being the same thing as this. If we cut it off from there to there and straighten it out, I would have cut the same distance. Or you can think of it as walking. I'm walking a straight line, but here I'm walking along a curved path, but the distance I walked is the same. Okay, when that happens, the distance here is also, right here, is also 1 unit. Right, so this is whatever 1 unit is for the radius, and then this is 1 unit for what we call the arc length, and we typically use S to represent the arc length. Okay, now when that's happened, when there's this 1-to-1 correspondence between radius and arc length, when they're both the same, then that angle that has been cut, we use the Greek letter theta a lot to represent an angle or an unknown angle. That angle that we've cut out is 1 radian. So that's what a radian is defined to be. It's the angle required to rotate from what we call the initial side and get to a stopping point at what we call the terminal side, and the arc length that's been cut out is equal to the radius. Okay, now I'm using 1. It doesn't matter what the radius and the arc length are. In general, the radian takes place when S equals R, when the arc length equals the radius, no matter what the radius is. I'm using 1 particularly because using 1 allows us to determine how many radians there are in a full circle. Okay, so that arc length is 1. I'm going to go all the way around the circle. If I go all the way around the circle and get back to where I start, how many radians would that be? Well, we know that's 360 degrees, but because it's also, there's this 1-to-1 correspondence between radius, radians, and arc length now, I can say that the arc length going all the way around would just be the circumference. And the circumference, remember the formula for circumference is 2 pi times the radius. Well, since the radius is equal to 1, the circumference is equal to 2 pi. And because the arc length is equal to the radian measure, the angle measure, there's that 1-to-1 correspondence, then that means that the angle required to go all the way around this circle of radius 1 is equal to 2 pi. Right. So what does that mean? Well, that means that 360 degrees is the same thing as 2 pi radians. Or you can clean it up a little bit more, divide both sides of this equation by 2, and you get 180 degrees, which would go from here all the way back over to here, but not all the way around. You'd be on the opposite side of the circle. And if I divide this by 2, I just get pi radians. So there's the identity that we use a lot to convert between these two angle measures. 180 degrees is pi radians. But the point here is this way that we measure angles, 1 radian, we cut out a lot of ground to rotate from here to here. 1 radian is much, much, much bigger than 360 degrees. Remember, pi is like 3.14. So 3.14 radians and 180 degrees. So there's a lot more degrees for each radian. There's a radian is much, much, much bigger and wider of an opening for an angle than a degree is. Remember, 1 degree is barely anything. We just barely rotate it up at all off of that initial side there. All right, well, what if the radius is not 1? Well, it's not like if the radius gets bigger that the angle is going to get bigger necessarily, because, yeah, the circumference would. If this radius were like 12, then this would be 2 pi times the radius. 2 pi times 12, 24 pi, but that's not going to be how many, it's not going to affect the angles. Now, why would that be? Well, think about if I put a bigger circle in here. I centered it at the same point, but I made a bigger circle. All right, so the circle got bigger. Well, this is still 1 radian. All I did is just extend those. That's still 1 radian, because notice I haven't changed the angle. That's still 1 radian, but the circumference, or the arc length is now much bigger than it was before. So no matter what the size of the circle is, there's still going to be 2 pi radians all the way around, and pi radians for 180 degrees. That's not going to change. So we have to come up with an adjustment to define the radian. It can't just be the same thing as the arc length, because the arc length does get bigger as we make the radius bigger. Okay, so what do? Well, we define a radian measure for any circle, not just a unit circle, which has a radius 1. We define the radian measure to be the arc length divided by the radius. So in ours, this was 1, this was 1, 1 divided by 1 is 1, right? But if we had, like we had here, if the radius was like 4 and the arc length was, in this case 4, because we're equal, then that's still going to be just 1 radian. 4 divided by 4 is 1. Okay, so that's how we make the adjustment if the radius is not 1. Instead of just the angle is the arc length, the angle is always the arc length divided by the radius. Alright, and then similarly, we can just take that equation right there, multiply both sides by r, and we got a formula for arc length. Alright, so you want to know the arc length, you want to know how much of a circle has been, or how much of the circumference has been traveled based on an angle. You just multiply the radian version of that angle, not the degree version, but the radian version of that angle, and multiply it by r, and that'll tell you how much of a distance has been traveled from the initial side. Alright, so here, just to practice it, a circle with a radius of 10 inches find the arc length intercepted by a central angle of 120 degrees. Alright, so that's 120 degrees, but look, we need to be in radian measure. So if I'm 120 degrees, and like we saw here, there's 180 degrees for every pi radians, I can write this as a fraction, 180 on the bottom, because I'm going to change from degrees to radians. I'm going to put a little RAD for radians. And then I can reduce this. This 120 and the zeros can cancel. I got 12 over 18. 6 goes into this 2 times. 6 goes into this 3 times. So that's 2 pi over 3 radians. Okay? That's what we need in the formula to come up with this. So S is equal to R, which is 10, times 2 pi over 3, which is 20 pi over 3, which is about 20.9 units. Or inches. That's our units here, the inches. Okay, so anyway, that's how we can adjust from, if we're giving us degrees, that's how we basically adjust from degrees to radians. If we want to go from radians to degrees, which we will several times in this semester, we just flip that fraction, put the 180 on top and the pi on the bottom, and then simplify once we've multiplied. Alright, angles in standard position. When we talk about standard position, we're dealing with the initial side being the positive x-axis, and we're rotating in the counterclockwise direction, and our terminal side is where we stop rotating. Alright, and then the angle cut is the angle that gets us from the initial side to the terminal side. Alright, if we rotate counterclockwise upward, that's a positive angle. If we rotate clockwise, if we rotate down this way to get to that terminal side, that's a negative angle. Alright, so there's an example of a negative angle that gets us down to the same place this was getting us to. Okay, we're getting to that third quadrant, but we're using a negative angle to get there. Alright, so here's a picture of the unit circle with positive angles rotating around, positive degree and their radian equivalent, and then negative angles rotating back the other way with their degrees and their negative radian equivalent. What I strongly encourage you to do is to look at this like a picture. Notice this is 30, 45, 60, and be able to come up with all of these radian measures without having to take too long to think about it. Not necessarily memorize them, but just notice the pattern here. Everything is 30 and 60, 45 degree angles in each quadrant. So 30, 60, that's 2 30s. 120, that's double of 60. 150, that's 5 of these 30 degree angles. But the thing I want you to see is the 150, that's 180 minus 30. So there's a 30 degree angle positive. Remember, going back the other way is a negative. That's a negative 30 degree angle, and 180 minus 30 is 50. So that's the same thing as pi, remember that's pi radians, minus pi over 6. So pi minus pi over 6, same thing as 1 pi minus 1 pi over 6 is 5 pi over 6. Right? 1 pi minus pi over 4 is 3 pi over 4. 1 pi minus pi over 3 is 2 pi over 3. Right? You're basically just like subtracting fractions. 1 minus 1 pi over 3, right? And then change it to a fraction is 2 pi over 3. Okay, we just took the pi's out. Right? Just, if there was a pi in there, it'd be 2 pi over 3. So you can get all of these special angles around here from these first quadrant angles. These are the key to everything, to understanding the unit circle, is understanding quadrant 1 and then symmetry. Alright, same thing. 180 to go down from here to here, that's positive because we're going counterclockwise. And how much did we go? We went the same as going from here to here, okay, because it's a that's a straight line going through there. That's a straight line going through there. So this angle is the same as this angle. So that's pi plus, because we're going counterclockwise, pi over 6. So 1 pi over 6. 1 pi plus 1 pi over 6 is 7 pi over 6. And again, you can get all of these values all the way around from these first 3 angles in the unit circle. Okay, this last quadrant, quadrant 4, the easy way to get those is to start from here and go backwards. So this is 0, but it's also 2 pi. Remember, I went all the way around as 2 pi. So 2 pi, but I'm going down pi over 6, so that's 2 pi minus pi over 6 is 11 pi over 6. 2 pi minus pi over 4 is 7 pi over 4. There's like this symmetry, this mirror going on here. And you can get all the special angles all the way around from understanding that first quadrant angles. Okay, you'll hear me refer to the quadrant 1 angles a lot, and all I'm talking about is the 30, 45, 60 degree angles in quadrant 1. We just flip those over into all the other quadrants to come up with the angle measures for all the rest of the unit circle. Alright, coterminal angles, because we could technically just keep on going around and around and around and around. We can add 360 degrees to any known angle and come up with multiple angles who would end up in the same place. They just may have spun around more than once. Think about like skateboarders or snowboarders or basketball players when they do those dunks or spin tricks on their skateboards. When they go around 720 degrees or whatever, they just keep spinning around more and more and more. So we could take any angle measure, that theta, and then add or subtract 360 degrees times k, where k is an integer, meaning just multiple times. So what that means is if I have a 60 degree angle like this, I can start off with 60, and then I can just add 360 as many times as I want to. Right, there's the 420, but I could do it again. And there's another angle that would get me to the same place, and another angle that would get me to the same place. And likewise, I could also subtract 360 over and over again and get angles that are now rotating clockwise, right, which are negative angles, which would get me to the same place. Negative 300 would be all the way around except the last 60 degrees, which would be right there. Right. So anyway, add or subtract 360 degrees over and over. Now remember, that's the same thing as 2 pi. 360 degrees is 2 pi radians. So if we have a measure in radian measure, we add and subtract 2 pi rather than 360 degrees. So for example, if I had pi over 4, it's a common radian measure. I don't put the pi in there. I just put, instead of pi over 4, I would write 1 pi over 4. So I'd put in 1/4, and then I'm going to add 2 pi. But again, I don't put the pi in there. I just put a 2. So pi over 4 plus 2 pi. Right, but again, the pi's are, it's kind of like I'm factoring out the pi's, combining the like numbers, converting that back to a fraction, because we write these as fractions typically, and then put the pi back in there in the numerator. So 9 pi over 4 is equivalent to pi over 4. So those are coterminal angles. So pi over 4 and is coterminal with 9 pi over 4. And likewise, I could keep doing that. I could keep adding 2, changing it back into a fraction. Alright, 17 pi over 4. Alright, or I could start off with pi over 4. Again, notice I just omit the pi. Subtract 2 pi. Again, I omit the pi. Math into a fraction. That's negative 7 pi over 4. So it's coterminal with 9 pi over 4. It's also coterminal with negative 7 pi over 4. Okay, so pi over 4 would be up here somewhere. All right, there's pi over 4. in radian measure. So what we're saying is that's the same as 9 pi over 4. Well, notice this is 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4, 9 pi over 4. I'm right back to where I started. And then likewise, if I went the other way, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4 in the negative direction. Okay, so there's an infinite number of angles that are coterminal with any given angle, just because we can keep adding and subtracting 360 or 2 pi as many times as we want to. Alright, so what if I gave you these two angles? Could you find a positive angle less than 2 pi that's coterminal with each one of these? So that's typically what we're after, are the positive angles that are in the first rotation, if there are any. So again, what I would do with you if I were doing a problem like this, 17 pi over 6. Now notice the 17, I'm omitting the pi again. That's bigger than 2, okay? So I need to subtract 2 pi, but again, I'm omitting the pi. So 17 pi over 6 minus 2 pi. Now, between 0 and 2 pi, change that back into a fraction. So that's 5 pi over 6. 0.83333 is 5. So 5 pi over 6 is coterminal with 17 pi over 6. Okay? And then negative pi over 12. So what do I need to do there? It's negative. I need a positive one, so I need to add pi over 6. Sorry, 2 pi. So negative, and again, remember, leave the pi off, negative 1/12. And then I'm going to add 2 pi, right, which is the same thing as 360 degrees. So I'm just rotating around, but I leave the pi's off. That way I can have the correct fractions. Alright, so there's 23 pi over 12. And that's between 0 and 2 pi. That's all we're after. If you ever want to check that these things are coterminal, what you can do, we haven't gotten into what they are yet, but we're going to do very, very shortly, the very next section. These are the trig functions, sine, cosine, tangent. You can verify that the sine, cosine, and or tangent all have the same outputs for both of these angles. Alright, and we'll talk about why they do once we get into that. So if I type in 17 pi over 6, alright, and these are radian angles, so I need to make sure my mode is in radian. Alright, if you're in degrees, switch it back to radian. So sine of 17 pi over 6 is this decimal. If I plug in the sine of 5 pi over 6, I'd want to make sure that I get the exact same thing. Alright, and I do. So those two things are coterminal. It's not necessarily coterminal yet. Again, we'll talk about why in the next section. But if we, it's not necessarily, this is not proof that they're coterminal until we have the sine and the cosine are both giving us the same thing. So if I did cosine of 17 pi over 6 is that, right? And then the cosine of 5 pi over 6, what we're saying is coterminal. Alright, then I get the same thing. So I'm getting a half for sine, negative this 0.866, negative 0.866. You'll actually know what that number is by the end of this course. I'm getting that for cosine, and because it's that for sine and cosine, that lets me verify that those two things are coterminal. Those are the same angle. Alright, again, we'll talk about why we needed to check with cosine and stuff like that later in the next section. But just know that's a way you can check that you do have something correct. It's just by sticking both angles into sine and cosine and showing you get the same thing for both in both cases. And that's a pretty good way to validate that you got the right coterminal angle, that you do have two angles that are coterminal by putting them in the sine and the cosine and showing you get the same thing. Alright, last thing here, linear speed, which comes basically straight off of arc length. Arc length is S. We use S as the angle times the radius. Okay, and that's giving us how much distance we've covered. And if we take that distance that we've covered and we divide by how much time has passed, then we end up with a rate of speed, right? Distance divided by time. Remember from your younger days, you probably saw this distance equals rate times time. Well, this arc length is a distance. Okay, if we take that distance and we divide by time, if we divide both sides of this by time, right, we get a distance divided by time, which is the same as this. That's a rate. Rate of speed. It's a speed measurement. So we get a linear speed that thing is traveling, like the tip end of this thing is traveling. When we divide the arc length by time, we get a speed that it's traveling along this path as it goes. All right, and then if we take the angle that's being opened up as time goes on, we get the angular speed, which is that internal angle that something it cuts out this path. So there's the angle that has opened up, and we're basically measuring how this angle is changing as time goes on. All right, the speed that angle is opening up over time. Okay, so this just notice this right here is r theta, so we can plug that in. We could actually write this as r theta over t is our linear speed, and then omega here is theta over t. So it's kind of like this divided by the radius. You know, if you want to look at it that way, we divided out the r, and that's the same thing as omega. All right, but anyway, let's look at this. What this is saying: a wind machine's used to generate electricity has these blades that are 10 feet in length. So that's 10 feet. That's r, right? The propeller is revolving at 4 revolutions per second. So it's spinning around over and over and over 4 revolutions per second. Right? Find the linear speed in feet per second at the tips of the blade. So right here they're giving us the angular speed kind of indirectly. They are telling us the propeller is rotating at 4 revolutions every second. Every second that goes by, we're doing 4 revolutions. Well, remember, a revolution from here all the way around back to here, that's 2 pi radians, right? And it's doing 4 of those in 1 second. So that's 4 times 2 pi, which is 8 pi radians per 1 second. All right. Well, that's the angular speed. That's W. Well, what do I want? I want the linear speed. All right, this is the linear speed, which we've got written this way, but notice this. That's V. So I could take V and multiply that by the radius, right? And that gives me the angular speed. So what we just found right here, angle divided by time, that's omega. I'm going to multiply omega by the radius, which is 10 feet, and that'll give me the answer we're looking for, the linear speed. So the linear speed is equal to the speed that we were just given, 8 pi per second, and multiplying that by the distance of 10 feet, the radius. All right, so we end up with the linear speed being 80 pi feet per second. Okay, so anyway, that's something that's a similar problem that you'll see in your homework. Just know that that's what's going on here. It's telling us the angular speed. So we use that fact, substitute in, and we've got the linear speed simply by just multiplying by the radius.